I'll turn it over to Richard Boyd, who's going to be walking us through our cooking session today. Thank you.
Okay, thank you very much. My name is Richard Boyd, and I'm going to be talking today about NLPQL expressions. I want to go through what the expressions are, the various expression types, and describe the calculations that go on behind the scenes that make evaluation of NLPQL statements possible. And after that, I'll give you an overview of a new tool we have that helps make syntactically correct NLPQL files much easier to create. All right, so to start things off, suppose you've been given the task of searching a corpus of radiology documents for lesions that have a size between 1 and 2 centimeters. Now, by the term lesion, I mean anything like a tumor or a mass or a cyst or something abnormal, something that shouldn't be there. I'm just assuming all that under the term lesion. And for whatever reasons, you're interested in finding lesions that are between 1 to 2 centimeters in size. So the question is, how can we use ClarityNLP to find these lesions in your radiology data? Well, from previous cooking classes and from having read our extensive online documentation, you'll know that you need to create an NLPQL file. You tell Clarity what to do by writing a file in a portable language called NLPQL. And since you want to limit your attention to radiology documents, you're going to need to create a document set that tells the system to only pay attention to the radiology files. You also need to create a term set that has lesion-related terms, since that's what you're interested in. You want to find measurements, so you'll need to run the Clarity Measurement Finder, which can locate the measurements and extract the individual dimensional components. And then, since you only want measurements of a certain size, you're going to need to write NLPQL expressions that filter the measurements that are found and return only the ones that you want. Okay, so let's walk through how we can go about doing that. So first of all, a word of advice. If you create a new NLPQL file, it's generally beneficial to limit the number of documents that you process initially. If you're like me, you'll probably have to iterate a few times to get it right. And if you have lots of documents, it could take a while to process all of them. So we have a limit statement. You say limit and then give it an integer number. Here I have limit 50. And that tells the system to process that many documents and then stop. So it's easy to iterate and change things and correct things and get the NLPQL how you want it without having to wait a long time for everything to run. Now, if you're looking for something that's fairly common, such as lesions or tumors or cysts on radiology data, then a small number, like 50 to 100, should be fine. You can find lots of results with a small number of documents. If you're looking for something that's fairly rare, you may have to process thousands or tens of thousands of documents before you find anything. So the limit statement is there, but whether or not it can help you really depends on the nature of your problem. Okay, so after that, there are a few lines of boilerplate. This is common to most of the NLPQL files that you'll write. You need a phenotype statement. It gives this file a name and a version. You can enter an optional description, and you also need to include the Clarity core libraries. So you have these 3 lines essentially in every NLPQL file that you create. Since we said we want to look at radiology data, we need to tell Clarity to focus its attention only on radiology reports. And you do that by creating a document set. And the statement here that I've got, this syntax will work for the Mimic 3 data. The reason it will work is because Mimic segregates various types of its documents, and it calls it radiology. It tags them with a capital R, radiology. So when we ingested these documents into our Solar collection, we mapped the report type field to the Mimic radiology label. Now, if you're using Mimic data, you can just use this statement verbatim. If you have another data source, then you'll need to alter this to use whatever syntax is appropriate for your installation. Okay, so after the next thing you need to do is create a term set. We want to find lesion-related terms, so we need to tell Clarity which terms to pay attention to. And this is where it's good to have domain knowledge or have a domain expert that can help figure out which terms are relevant. So here's a list I came up with. I don't have any medical background, but I've looked through lots of radiology reports, and terms like this seem to be used a lot. This is not a comprehensive set by any means, but it's good enough to find about 150 or so measurements in 50 documents from Mimic. Okay, so we want to find measurements, so we need to run the measurement finder. And this next statement tells you how to do that. It says, activate the measurement finder and turn its attention to the document set listed here as we call docs, and pay attention to the terms in our lesion terms term set. And if it finds any measurements, it will return each one tagged with this string called lesion measurement. And this string is used later in the constraints that we'll write, and it will show up as well in the result files that we'll look at. Now, I want to find patients that have these lesions, so we need to set the context. And to focus on patients, we set the context to patient. There's another context called document if we want to do a document-centric search, but we want to find the actual patient IDs, so we set the context to patient. All right, with that out of the way, we can now write NLPQL expressions that impose constraints on the sizes of the measurements that we want. And I should say here at the outset, when Clarity finds a length measurement, it will normalize all the units to millimeters. So our original problem statement wanted lesions from size 1 to 2 centimeters. Well, 1 centimeter is 10 millimeters, 2 centimeters is 20 millimeters. So the 1 to 2 becomes 10 and 20. That's why you see 10 and 20 here. Also, sometimes in the radiology data, it'll say it's found it'll state a measurement size and say it's one-dimensional. Other times you'll have 2 dimensions reported. Other times you'll have 3. So if you want constraints on all dimensions, you have to explicitly state which dimensions have which constraints. So that's why I have a 1D, a 2D, and a 3D defined statement that impose our constraints on each measurement component. Now you'll see the term lesion measurement here. This comes directly from the tag we gave our measurement finder results up here. Okay? This says for every lesion measurement you find, check its dimension X field. If it's greater than or equal to 10 and less than or equal to 20, then generate a new result and give it this tag X between 10 and 20 millimeters. Similarly, if you find a 2-dimensional measurement, you can constrain both X and Y, and if it passes these constraints, tag it with XY between 10 and 20 millimeters. Similarly for XYZ. If you're wondering, how did I know to use dimension underscore X, dimension underscore Y, and Z? That's because that's the name of the fields that the measurement finder generates for its results. And you can check our measurement finder API documentation. I can go up here. So we have documentation on all our API components. And for the measurement finder in the results section, you scroll down, you'll see dimension X, Y, and Z. These are the numeric values of the actual numbers it finds in the measurement text. So the X dimension is reported as dimension X, similar for Y and Z. Now I should also say that if there's only one number listed, it will always be returned as X. So you never get a Y without there being an X. And similarly for the Z component. All right, so those are our constraints. And so I can collect everything together into one file here, and so you can take it all in at once. So I think I'll pause here for a minute and ask if there are any questions about this NLPQL file so far. Okay, hearing none, we'll soldier on. So now the next thing to do is we like to run this. But I would highly recommend that before you try to run it, you first check it for syntax errors. And conveniently, we have an API endpoint that will take your file, parse it, and report back if it finds any syntax errors. And normally when you submit a job to Clarity, you do an HTTP post to an API endpoint. So we have an endpoint called NLPQL tester that will do this syntax checking for you. So in previous cooking sessions, we showed you how to use a graphical tool called Postman to do this HTTP post. Today I want to show you another way to do it using a command line tool called curl. Curl is open source software. It's been around a long time and has gobs of features that can do anything you could possibly want to do with HTTP. So this curl command here is what you would use to submit your NLPQL file to our tester endpoint. So I'll point out a few highlights of this. The -x post, that specifies you want to post the next URL. You want to post the file to the following URL, which is NLPQL_tester. The H argument tells you to set the content type to text plain. This is just plain text. It's not JSON or anything else. You need to prevent curl from trying to interpret the file, and that requires this data binary option. Even though the data is not in binary format, for some reason curl called it data binary. So if that flag is present, it tells curl to pass the file through without trying to interpret the contents. And the final part of this is the path to your file. So this curl command assumes it was issued from the same folder that the Legion NLPQL file is in. If that's not the case, you need to specify the path with syntax like this, okay? And you need that strange @ sign prepended to it. That's just another quirk of curl.
Richard, you may also want to note for people that want to use the graphical user interface, the earlier, I think the first session of Cooking with Clarity gives guidelines how to use the GUI, not Postman, but the Clarity GUI.
Yeah, the Clarity results viewer.
Right. Okay. All right. Thanks. Okay. So I have a command window here with this command in it. If I submit the command, notice it generated a lot of JSON data as a result. That's the result you will get if the syntax is correct. Okay. And this is essentially the JSON representation of your NLPQL file. If your file had syntax errors in it, it would report errors and possibly give you a Python stack traceback as well. So since we got JSON result back, everything's okay and we can proceed. So when I tried to run this in this notebook, and for some reason I didn't get all the data back. I don't know exactly why, but if you run it in the command window, you will get the data back. All right, so now that the syntax is correct, we can actually submit the job to run it. And to do that, you'll use an identical curl command, except you'll now do the post to the NLPQL endpoint. That's all you have to do is just change NLPQL tester to NLPQL. If you submit that job, I won't do it now during this session. It takes a few minutes to run. But I put a result file that it generates in the assets folder of our repo. So if you go to the, if you go to our GitHub page in the Notebooks Cooking folder, you'll see this folder called Assets. If you scroll down in here, there's this file legionintermediate.csv. And that contains the intermediate results that were generated from running that NLPQL file. So I've got that file here. What is this thing?
It's the WebEx.
Yeah, okay. So here's the file with the results. You get a lot of fields and a lot of data. I have a condensed version of this in the notebook, and I'll just use the notebook to walk through this. But if you want to see everything, you can take a look at that spreadsheet. So here are the results that it generated. From our 50 documents in Mimic, looking for that term set that we provided, we found 194 rows of data. Now, I should say here, one row in this spreadsheet equals the equivalent of a single result document in the MongoDB database. Okay, all the results get written to Mongo, and each result is an independent document. And this term document is used in the MongoDB sense, meaning a collection of key value pairs. So down here below, I've got an example of one of these documents. I picked row 2 and extracted it from the database and then printed it here into the notebook. And this is everything that's in a single measurement result that Clarity found. Okay? You can see dimension X, Y, and Z, and all this other data. Extracted all that stuff in this measurement. But the spreadsheet essentially flattens all that out for you and presents it in a format that's a lot easier to view. So, and the columns here, you'll see dimension X, Y, and Z. These are the dimensions of the measurement it found. You'll see these NaNs showing up also. This means not a number. And the measurement finder actually returns the Python none value if there is no dimension given for that measurement. So if you look at this first one here, we can go to the spreadsheet, and it reports the sentence where it was found. So the sentence that it found said non-FTG average speculated 2.8 by 1.6 centimeter. And whatever that means, it was 28 by 16 millimeters. So we go back to the results here. We found 28 by 16, but there's no Z component. Okay, so Z component came back null, and Jupyter just converts it to not a number here in the notebook. All right, you also see a job ID field. Each time you submit a job to Clarity, a unique number is assigned to that run. And this is the way that the system distinguishes the results of each run. And this will be very important later on when we get into how to do filtering and all that as part of the evaluation process. The NLPQL feature column is also very important. Here you'll see a lot of rows, a lot of entries that are tagged as lesion measurement. Okay, these are the results, the raw measurement results that come from running the measurement finder. Okay, because we gave it this string lesion measurement and said anything that it found will be tagged with lesion measurement. So here it is reporting all the results that it found. And these measurements were extracted without any knowledge of the constraints. So you can see here, here's one that's 110 by 101. That's much bigger than 10 by 20 that we're interested in. Now, these are the raw results before any constraints were applied. Okay, and scrolling down, we can see the measurements that it found that it claims satisfy the constraints. So the rows tagged X between 10 and 20 millimeters. Anything here in the first column for all these rows should be either greater than or equal to 10 and less than or equal to 20. And if you look at all these, you'll see that's indeed the case. Now, some of these measurements have Y and Z components that are outside of that range, but that's okay because these result rows were obtained by evaluating a constraint that was only applied to the X dimension. So if you scroll down some more, there's another set of rows where we had constraints applied to X and Y. So both these first two columns here, there should be nothing in either of them that's less than 10 or greater than 20. And you can see that's also the case. There's one here, the Z component, that's 7, but again, the constraints are only on X and Y, not Z. Finally, the last row here has constraints applied to X, Y, and Z. And it found only one of those. Okay, so this final field here is subject. We set the context to patient. That means we want to know the patient IDs that had these measurements. And that's what this field is. The patient ID is actually stored in a field called subject. So here you can see the first 4 lesions that were reported all applied to this patient number 4463. Here's the next patient had 3 lesions. Here's 1. Here's another patient that had a lot. Okay, so the actual results we're looking for, the patient IDs, will be a subset of all of these tagged with the lesion measurement string. All right, so to summarize all of this, when you do a run with Clarity, the intermediate results file that you get contains a representation of the data that's been written to Mongo database. Each row is an independent, separate result document that either results from a task being run, such as the measurement finder, or is the result of a computation from an NLPQL expression. And I have text to that effect down here in the notebook. All right, so I think I'll pause here once again and ask if there are any questions about any of this before I proceed. Okay. All right, we'll continue on then. So now let's talk about NLPQL expressions themselves. So there are 2 types of NLPQL expression. One type we call mathematical expressions, and another type we call logical expressions. And they're rather different, so I'd like to discuss what the differences are. So here's 2 examples of mathematical expressions. These are found in define statements, and the expression part is everything after the where keyword. So for this has fever, the temperature dot value greater than or equal to 100.4, the highlighted piece here is the actual expression. For this one that we've seen, this is our X constraint. The expression is all of this stuff. All right, mathematical expressions can be identified because they involve numeric literals such as 100.4 or 10 and 20. They involve mathematical operators like greater than or equal to, etc. And they involve tokens of the form A dot B, where the A part is an NLPQL feature and the B part is a field name of a result in the Mongo database. So temperature dot value, that's definitely an A dot B expression. NLPQL feature temperature B value. Here, lesion measurement, that's another NLPQL feature. And the two field names are dimension X and dimension X. Okay, so anytime you see an expression of this A dot B form, you'll know that's a mathematical expression. And the reason these are important is because they operate on data contained entirely in a single result document, or equivalently a single row of the spreadsheet that we were just looking at. So you can't have something like temperature dot value and also in the same statement blood pressure dot systolic. Okay, that's not going to work because those are two different NLPQL features. Mathematical expressions can only use a single NLPQL feature, meaning a single row or a single result document. All right, logical expressions. This is the other type. You also find them in defined statements, and they're also the part after the where keyword, such as has fever and has sepsis symptoms. Okay, these expressions involve the logical operators and, or, and not. And unlike the mathematical expressions, these things operate on the NLPQL features themselves. They're essentially a higher level construct that operates on sets of rows in the CSV file, or equivalently on sets of documents in the result database. Okay, so the mathematical operations that operate on single rows, we call those single row operations. Logical expressions are called multi-row operations. And there's another further constraint on these things, in that you can't use parentheses in these expressions. So here's an example. Here's one that involves and or, called my logic feature, where A and parentheses B or C. So you may know why we can't evaluate this as written, because that would mean, first of all, we'd need a set of rows tagged with, who have the NLPQL feature tagged as A. We need another set of rows with their NLPQL feature set to B, and another set of rows with NLPQL feature set to C. But this parenthesized expression, B or C, there's no explicit set of rows in the database that has the result of doing that evaluation. And right now, Clarity to do this by like generating an temporary tag and writing the results out and then reevaluating the original expression. We can't do that. Maybe we'll have that at some point, but we can't do that at the moment. So if you have a complex logic operation that requires parenthesization and more complexity, you'll need to synthesize it from simpler operations. So you could evaluate this by first evaluating the B or C part and explicitly giving that an NLPQL feature tag, and then explicitly including that in a logical operation where you take the logical AND with A. Okay, so you have to compose complex logic with simpler pieces. Okay, so let's talk about how you can evaluate these things. So how does a single row or a mathematical expression get evaluated? Well, the first thing it has to do, after the parser parses the expression, it has to figure out which NLPQL feature you're using and what the field names are. So that's pretty simple. It just splits it on the dot, and it checks it to make sure there's only one NLPQL feature. If there are more than one, it returns an error saying it can't evaluate it. So these two examples here, the NLPQL feature is temperature and the field name is value. For the next one involving lesion measurements, the feature is lesion measurement and the field list contains dimension X and dimension Y. So to do the evaluation itself, we use something called the Mongo aggregation framework. And the reason for this is that the data is sitting there in Mongo itself, and we'd like to make the evaluation process as efficient as possible. If we used another library, and if the Mongo instance were hosted remotely, we'd have to do queries to extract the data from Mongo, transmit it across the network to whatever machine is running the evaluator, ingest it, do the evaluation, transfer it back, and then insert it back into the database. That could be a slow process if you have lots of data. So if it's possible to do the calculation entirely within Mongo itself, that's preferable. It turns out it is possible using something called the Mongo aggregation framework. And that is a capability provided by Mongo that lets you filter documents, transform them by adding fields or removing fields or calculating things and assigning them to field values, etc. It's a general way to transform documents set up as a pipeline of operations. So we do this, and the first stage in our pipeline of operations is to do a filtering operation. So we mentioned the job ID previously, saying every job is assigned a unique ID. If we're evaluating an expression, we only want to focus our attention on the data for that particular job. So we have to filter on the job ID initially. And then for the fields we want to use, such as NLPQL feature and these others in this field list that we just mentioned, we have to check that they actually exist and that they're not null, because you can't do calculations with null field values. So an existence check alone is not sufficient. Okay, a null field exists, but it has a value that can't be used for calculation. So we have to check all these things in the initial filter stage. And this text here shows you what the syntax is. You don't have to know this syntax, but you can sort of get the gist of what's going on. The $exists means that if the field exists, is true, meaning the field exists. NE means non-equal, and if it's not equal, okay, that's how you specify these filter constraints on these fields. All right, so the first stage of the pipeline is to do a broad-phase filter on the job ID and to check for the existence of the actual variables you want to use. Okay, after that, we do a conversion of the expression from infix to postfix. We want an automated way to evaluate this, and it's much easier to evaluate a mathematical expression if it's in postfix form than if it's in infix. And the main reason is because infix can use arbitrary parenthesization, and that can be kind of complicated to process in an automated way. So we do this conversion to postfix. It removes all the parentheses, and we can use a simple stack-based evaluator to generate the commands we want. And when we do the evaluation, we don't actually compute the result. Instead, our evaluation process involves string processing that generates commands that are sent to Mongo that tell it how to compute the result. So for the temperature.value example, you can see that what's going on here roughly. GTE means greater than or equal than. $value refers to a field name. So this says if the value field is greater than or equal to 100.4. That's what that means. Here the next one says if the NLPQL feature equals temperature, etc. Okay? The projection just brings the result of that out into a new document, and it's a Boolean value. So the result of all this evaluation is a set of new documents that have Booleans that are set to true if the original document satisfied the constraint. Okay? And then we do a simple query for those documents and return those as the result. So are there any questions about this Mongo aggregation pipeline and how the mathematical expressions are evaluated with it?
Yeah, and I just wanted to restate that this just kind of digs into how Clarity works and how Clarity processes these expressions. But if you're just using ClarityNLP as like a high-level user, you don't necessarily have to know all this syntax. It's just more like the syntax we showed above. This is just sort of digging into how we process and how we come up with results.
It shows all the hard work that you don't have to do by writing the high-level queries and what's going on underneath the hood.
Yep.
Right. Okay, So what do we need to do to evaluate the multi-row or logical expressions? Okay, these again apply to the logical operators and or not, and they operate on sets of result documents. So an example would be here in this defined statement has no z constraint. Okay, this does a logical OR between two sets, one set being all the documents, all the measurements that were found that satisfy the constraint on x, and all the measurements that were found satisfying the constraint on both x and y. So the not operation we use for set differences. We don't support just a unary not operation at the present time, because that really opens up a can of worms and could involve lots of calculations that we just don't support yet. So a logical not is used to do a set difference. So this example has sepsis symptoms without rigors to be where has sepsis symptoms not has rigors. So A not B essentially means find everything that's an element of set A that's not also in set B. Okay, can't do unary not. So to evaluate these, we use the Mongo aggregation framework again. The initial operation is a broad-faced filter on the job ID and checks for the fields and that they exist and aren't null. Okay, we toss out any documents that have NLPQL features that we're not interested in. And the ones we are interested in are the ones that are being ANDed or ORed or knotted together. Okay. Then after that, the documents are grouped by the value of the context variable. So if we're in a patient context, which for our example above, that's what we were looking at, we would group the remaining documents based on the value of the patient ID. So essentially, the remaining documents that pass the filter would be grouped according to which documents apply to which patients. Okay, for a logical AND, there has to be an additional operation applied. We count the number of documents in each group, because an n-ary AND, if you have fewer than n documents, that couldn't possibly satisfy that condition. So any groups with fewer than n are tossed out. Similarly, any groups that have less than n distinct NLPQL features are also tossed out because they couldn't satisfy the constraints either. After that, there's a sorting process applied that sorts by the value of the other constraint that we didn't use. So if we're in a patient context, the remaining documents will be sorted on the document ID field. This just breaks them further into subgroups and helps with operations down the line. So for logical OR and not, that's essentially all we have to do, because the remaining documents in the group satisfy the constraints. And those are written out and returned as the result. For n-ary logical AND, we group them into n tuples, and the n tuples form members of they're essentially a subset of the full inner join result that you would get by doing an n-ary inner join on the sets in your expression. Now, you do not have to compute a full inner join to get the results you want, because you already know the value. So for instance, in a patient context, we want to know patient IDs. We already know the values of the patient IDs because we grouped them in a previous stage. And so I don't have time to go into all this now, but just take my word for it. You don't need to explode everything into a full inner join. That could generate hundreds or thousands of rows in the output. It's just not necessary to find the patient IDs that you want. Okay, I'll probably have more to say about that in future cooking classes, but for now, just take my word for it. Okay, so that's all I really wanted to say about evaluation of expressions. We've got two types of expression, mathematical and logical. They're computed in somewhat different ways, but they both use the Mongo aggregation framework to do the evaluation. So before I proceed to the editor, are there any questions about any of the things we've covered so far? Or any comments? How are we doing on time here?
20 minutes left.
Okay. All right, so we have an NLPQL editor tool that really helps make the process of NLPQL generation much simpler. So in this notebook, I have a walkthrough and a write-up with lots and lots of screenshots showing you exactly what you need to do to use it to generate the NLPQL file that we started this notebook with. Okay, so if you it's laid out here step by step. So let me just demonstrate this to you in the editor itself and show you how it works. So here's the editor, and this at the right here is just an edit window. You can type text into it just like you could into a text editor. On the left here are command buttons, and you press these buttons and they pop up forms that you enter data into, and then when you save it, it generates NLPQL commands in the editor that are syntactically correct. Okay, over on the right here, the clear button, if you mess up and want to start over, just press clear. And the copy to clipboard button, when you are finished creating your NLPQL, you can click that button, copy to the clipboard, and then paste it into a text editor. All right, so let's walk through how we would create our NLPQL file. So notice that some of these buttons are grayed out. They're not activated yet until you create the phenotype name and add the Clarity libraries. So we call this phenotype lesions 1 to 2 centimeters. And then we give it a version. Let's call it version 2 since it's the second one we're doing today. Click the button and it inserts the expression straight into the editor. Then we need to add the Clarity library statement. Click the button, it inserts the include just like that. We had a limit of 50 documents, so we can click the limit query, type in 50, accept it, and it inserts the limit statement. So it's very easy to create NLPQL using this editor. The next thing we have is a document set. Let's see. There's several choices to create this document set. The one we want is the Solar query by report type. So we call our document set docs, and we said we're interested in report types of radiology. And again, you would use whatever syntax is appropriate for your installation. And you can also specify things like report tags and all, and give it custom Solar queries. And this is all documented in our API documents if you want more info about what all these other fields mean. So save changes, and lo and behold, it inserts the document set statement that we had before. Then we had a term set of various lesion terms. So we called it lesion terms, I believe. And then we had terms such as lesion, growth, mass, cyst, etc. You can type in all the terms here, save your changes, and it will insert the term set that you had. Now, it looks like I made a mistake there, but this is an edit window, so I can just go back and fix it. Okay? Then we set the context to patient. So here's the context selector. We have patient or document, patient to default, save changes, and there we get the patient context. After that, we had, let's see, we need the measurement finder. So remember we had NLPQL features. The measurement finder is something that generates features, so we'll find that on the define feature button. Here we have all the algorithms that we can support so far. We choose measurement finder. We call them lesion measurements. Measurement. And told it to use our term set that we call lesion terms. Our document set that we call docs. We're not using the Odyssey cohort or anything else. So save changes, and there's our measurement finder. And finally, we need to add the constraints that are our NLPQL expressions. So those are under this define results button, because those can generate results independently of any featured tasks. So our result name, the first one was, let's see, X between 10 and 20 millimeters. And then we entered the logic for this, such as lesion measure X, can't type today for some reason, greater than or equal to 10, and measurement dot
It's worth noting that
y
the logic is going to be driven by what's returned, and so the documentation for each API would provide you with what the output would be from your features.
That's right.
That's really the only way to know what logic you can use.
Yeah, if you look at the API specific doc in our on the Read the Docs site, it will give you specifically what each API, what each feature returns. So you'll have basically all the values that you can join on and do the sort of like either the mathematical operations basically. So
right, we mentioned the measurement finder earlier. So here's the documentation of the measurement finder. And I mentioned, using dimension X, Y, and Z. Here it is in the results. The measurement finder generates results, and each number that it finds is called X, Y, or Z. So they're right. You have to check the API docs to know which fields to use. Now you notice when I did this, it tagged it with the final keyword. What final means is if you're not interested in all the intermediate results, it will write the final results to a separate CSV file. I didn't use final before because I wanted everything in one place to look at it all. So you can just delete the final word here, and this dimension Y should have been dimension X. And that reproduces our original X constraint, okay? And then you can repeat the process for the XY and XYZ, or just cut and paste in this edit window, whatever is easiest for you. So basically just a few keystrokes and filling in a few forms, you can reproduce that NLPQL file that we started with. And when you get it in a finished state, just press the copy to clipboard button, click OK, then bring up a text editor and paste it in. And there you go. You can save it and then run it by posting it with the curl command or using Postman or whatever you like to use to do HTTP.